also define what it means to be in series and parallel for a circuit element. So let's start with our learning goals. Our learning goals are to understand and be able to apply Kirkhoffs voltage law to an electrical circuit, to understand the definitions of series and parallel for circuit elements, and number 3, to understand and be able to apply Kirkhoffs current law for an electrical circuit. Alright, so let's begin with Kirkhoffs voltage law. So I'm just going to write it as KVL. That says the voltage drop around a closed loop is 0. So what that means is if you start and stop at the same point but go in a loop, that the net voltage drop will be 0. So let's do a simple example. So let's have a voltage source connected to a resistor. This has a voltage V across it, resistor R right there. So if we now, and let's say this is the positive side, negative side, there's going to be a current I this way, and let's now go around and do the voltage drops. So we can pick this point right here to start. So as we go along with the current, we go from high voltage to low voltage across the resistor. So we're going to get a positive VR because we did a voltage drop. We went from high potential to the low potential. And now when we start to finish the loop, we're going to go from the low potential to the high potential. So that's going to be a negative drop across the battery. So this is VR minus V equal to 0. And this is Kirkhoffs voltage law. So we can redraw this as sort of an altitude type thing. So if we have our ground right here, this is V equals 0, and then this comes up to a height that corresponds to V. What happens as we go across the resistor, we drop down in voltage to the bottom potential. So this is now V sub R, and this is what our loop would look like. We're starting up here, going down in voltage, and then once we get to the voltage source, we come back up. So our net change in height is 0, so that's exactly what we wanted. All right, let's go on to a little bit more complicated example. So if we instead have still a voltage source, and we're going to have 2 resistors. So this is going to be V, this is going to be R1, this is going to be R2. If we do and forgot to write down that we're going to have current I flowing through the circuit. If we start up here and do a loop, come around, back. So the first part is V sub R1 plus V sub R2 minus V equal to 0, or the voltage from the voltage source equals the voltage across the resistor 1 plus the voltage across resistor 2. Schematically, in a little altitude type picture, we'll have this be our ground, so V equals 0. We're going to come up to some height V. Now the voltage drop across the first resistor is V sub R1, and then the voltage drop across the second resistor is V sub R2. And if we do a loop, we see that we start up here, high voltage, we go 1 voltage drop, 2 voltage drop, we're now down here, and then we go back up to where we started. So what we can see is that in this case, the resistors are acting as voltage dividers. So we start off with some potential, and then we follow the exact same current through resistor 1 and resistor 2. So in this case, the resistors are acting to break up the voltage. And the reason why is because the same current that goes through R1 goes through R2, and that defines series. So series has same current. And resistors or circuit elements in series are voltage dividers. So that means the voltages will sum rather than all being the same. So dividers. All right, so let's do a slightly more complicated example. So if we have now a potential source, resistor V, R1, and then we have another resistor over here, R2, and that's connected. We're going to have current I, and then each one of these will have a current I1, current I2 flowing through them. So we can go ahead and do some loops. So this will be the first loop. So we can start right here. We can go down here. So that's going to be V sub R1. And then we can follow this over. And then we'll go back up to V and back where we started. So minus V equal to 0. So this is the first loop. We can do another loop on the outside. So if we go this way, we'll go minus V, keep going on the outside. Now we go down this resistor, so it's plus V sub R2, that equals to 0, and we'll finish up down here. Notice that we didn't go across resistor R1, we just went around it. And then the third loop that we can have is, so red was number 2, and then we can do a third loop. So we can start off up here, go down resistor 2, so that's V sub R2, and if we go back up against the current for resistor R1, then that is a negative voltage drop, so we now have minus V sub R1, and that equals to 0. So from loop 3, we see that V sub R2 equals V sub R1. And this is the definition of parallel. If two circuit elements have the same voltage across them, then they are in parallel. So we can draw a little schematic of this. So we'll have the ground right here. We'll go up some height V. So we go up V potential. And then we can go down this way, which will be V sub R2. Or, so the whole thing about parallel means you have options. So you could either go down R2 to get to the negative terminal, or you could go down R1. So now we go down V sub R1, and then we can just draw on our loops. So this is loop 2. This is loop 1. And then our loop 3 is like that. All right. So now we can go, so that's more or less Kirkhoffs loop law and voltage law and how you can apply it. And now we can go and look at the exact same scenario and look at Kirkhoffs current law. So we're going to have V is going to be R1. There's a total current I. There's a current down here. I1, and there's another current over here. This is R2, and that's I2. So Kirkhoffs' current law just says that at a junction, the current coming in equals the current that leaves. So what's a junction? Junction is where wire comes in and splits off. So we have two junctions right here. So at this junction right here, so we can label this as junction 1. The current coming in is just going to be I, and then the current going out is just going to be I1, because part of it comes down here, plus I2. So what this says is I equals I1 plus I2. And then if we wanted to, we can look at this junction right here. And what we see is I in equals I1 plus I2. And then I out equals I. So I1 plus I2 equals I. So Kirkhoff's current law is really just a statement of conservation of charge. We have the amount of charge coming into a junction, and then the amount of charge that leaves there is the exact same. All right, thank you very much.